Okay, so we're very excited to have our first speaker, Nati Seiberg. Nati did his undergraduate studies in Tel Aviv University, and he moved on to do his PhD at Weizmann Institute in 1982. Nati was a professor at Weizmann and then at Rutgers, and since 1997 he's a professor at the Institute for Advanced Study in Princeton. His research focuses on various aspects of string theory, quantum field theory, and particle physics. With collaborators, he found exact solutions to supersymmetric quantum field theories and string theories that have various applications to mathematics. I went through Nati's CV and found 32 awards, but I could only identify one which is truly important and prestigious. This is the IPS prize that he got received in 1976. I have no doubt Nati is very proud of that. Of his less prestigious awards, you could find the MacArthur Fellowship in '96, the Danny Heinemann Prize of Mathematical Physics and of the American Physical Society and the American Institute of Physics, the Breakthrough Prize in Fundamental Physics that he received in 2012, and the Dirac Medal that he received this year. Nati is a member of the National Academy of Sciences and a fellow of both the American Physical Society and the American Academy of Arts and Sciences. And today, Nati will tell us about symmetries, duality, and the unity of physics. Nati. עכשיו צריך למצוא את זה.
לא בסדר. זה לא זה. זה, אני לא התחלתי את הפרזנטיישן. זאת הבעיה שהייתה קודם.
מה זה היה הפונקציה שעשית קודם?
זה לא שייך, הוא לא מקבל את הסיגנל מפה. הוא מקבל את הסיגנל מהשני. עוד לא התחיל הפרזנטיישן, תראה, נסגור אותו.
גם זה לא?
Okay, can you hear me? So first of all, I want to thank Tomer for the wonderful and generous introduction. I also want to thank everybody for coming in this rainy day. And most of all, I want to thank the organizers here for putting together such an interesting conference and for inviting me to speak here. As Tomer said, I was an undergraduate here in Tel Aviv, so it's particularly exciting for me to be back here in Tel Aviv. It brings nice memories from 2 or 3 years ago when I was here. The talk will have 3 parts. I'll talk about symmetries, duality, and the third part will be on the unity of physics. It will be kind of a very broad brush talk covering many, many topics, and there was just no way to give references. So by and large, I will not have any reference except one slide where I'll mention some recent work. So I'll start from the beginning and talk about symmetries. So if you Google symmetries and you look for nice images, what you see is a Taj Mahal, and if the projector here had better quality, you could have seen how beautiful it is. And it's really very symmetric, but then I realized that a much more symmetric object is just the Star of David. It's a simpler pattern with a lot of symmetries. Now, physicists love symmetries. I fell in love in symmetries when I was an undergraduate here, and I took a quantum mechanics course with Amnon Aharoni. It was a really spectacular course which emphasized the role of symmetries in physics, and it had huge impact on myself and on my career. And later I learned that that class was based on notes Amnon took in a course he had taken earlier by Raqqa in the Hebrew University. So the roots of symmetries go really deep. The history of symmetries that physicists are interested in. There is the Galileo symmetry and Lorentz and Poincaré symmetry. That was early on. And then there's the issue of crystallography. It's kind of another symmetry of space and time. So these symmetries that we talked about so far, Lorentz symmetry or crystallography, are symmetries that we move objects in space or in time. More modern developments in the 20th century led to flavor symmetries or global symmetries like isospin that relates the proton and the neutron. And again, a development that happened partly here in Tel Aviv University is SU3 that combines also the up and down and the strange quark into one multiplet. It was later realized that a much deeper concept is the concept of a gauge symmetry. And the first example of that is in Maxwell theory, where the vector potential A mu can be shifted by a derivative of a function of space, lambda. And lambda can depend on x, so it's an arbitrary function. And the theory is invariant if we just make such a transformation. There is a cousin of this gauge symmetry in general relativity, where we transform the metric in a similar way, where this function xi is again a time function that depends on x. In fact, these are four functions that depend on x. And the key thing here is that both lambda and xi depend on x, so we have a transformation where the transformation parameter is not just a number, but it's a whole function, or several different functions. And indeed, later on in the 20th century, this concept of local or gauge symmetries became fundamental in the standard model of particle physics. First, the existence of SU3 of color, and then in the whole standard model of particle physics based on the weak interactions with SU2 times U1 and the same SU3. So that's very nice, and such gauge symmetries are supposed to be very deep. So first of all, it's a huge symmetry. Unlike ordinary global symmetries, where we have just one transformation parameter that is independent of x, in the case of gauge symmetry, the transformation parameter depends on position. So we have an arbitrary group element at every point in space-time. So this is a huge symmetry group. We have an arbitrary group element in every point in space-time. So that's the first sign that it's deep because it's so big. Second, in the context of electrodynamics, it's an extremely useful symmetry because it makes the theory both manifestly Lorentz invariant, unitary and local, and therefore causal. All these are things that we really love and cherish, and we would like to have them in a good theory. And the gauge symmetry of the model is what enables us to do that. And it appears in many applications. I've already mentioned Maxwell theory and the standard model of particle physics. I also mentioned general relativity, but it's also extremely common in condensed matter physics. Some of the ideas that we heard about earlier, even today, about topological superconductors and topological insulators, depend on having such gauge symmetries. And finally, it is associated with deep mathematics. In mathematics, the idea of fiber bundles is crucial, and all that are consequences of gauge symmetries or manifestations of a gauge symmetry. So this is really the hallmark of a deep idea. A deep idea in physics is an idea that has many implications, that connects to different branches of physics, maybe even to mathematics, connects to notions or directions that we didn't anticipate before. So that's the hallmark that something is new. We try to do to solve one problem, and the solution also solves many other problems. My favorite example of that is calculus. Newton invented it to describe the motion of bodies, and later on it turned out to have many applications, even in the social sciences. So all that is just to say that gauge symmetry is very deep. It satisfies the hallmark and the test for a deep idea. But, and there is a huge but here, because of Gauss' law, the Hilbert space in quantum field theory or in quantum mechanics is actually gauge invariant. So all the states in the Hilbert space do not transform under the gauge symmetry. Therefore, the gauge symmetry is not really a symmetry. It doesn't act on anything. All the operators in the theory, operators that appear in the quantum mechanical system, are gauge invariant. So what kind of a deep idea is that? That it's a symmetry that doesn't act on anything, and everything doesn't really transform under it. So a better phrase is to say that this is not a symmetry, but it's a redundancy in our description. We have many different redundant descriptions, and the redundant description is useful, but it should not be viewed as deep. This brings me to the next topic I'd like to discuss about symmetries. I'll later put all of these separate things together, and that's the idea of emergent symmetries. So global symmetries can emerge and appear as accidental symmetries at long distances. So we have some fundamental theory at short distances, and at long distances, we can have more symmetries that we did not put in by hand or do not exist at short distances. Such symmetries are essentially approximate. They have to be approximate symmetries because the fundamental theory doesn't have them. This is an accident that we see at long distances. And there are many examples of that. In the real world, parity is a symmetry, time reversal symmetry is a symmetry. But fundamentally, in the standard model of particle physics, these are not symmetries of nature. At short distances, nature is non-invariant under parity and time reversal, and yet they appear as approximate symmetries at long distances. Similarly, the stability of matter, of protons, for example, relies on the symmetry, barrier number symmetry. But again, this is just an approximate symmetry. It's not a fundamental symmetry of nature, and therefore it cannot be an exact symmetry. So that's for emergent global symmetries. Exact gauge symmetries can be emergent. And again, I mentioned the examples in condensed matter physics where emergent gauge symmetries are extremely common. And one way to understand why they have to be exact is that they are not really a symmetry. This is a redundancy, and the redundancy is always exact because otherwise it's not a redundancy. In other words, to summarize this slide, we have global symmetries and gauge symmetries. Gauge symmetries are not really symmetries. It's a bad terminology. They can be emergent. The global symmetries, if they emerge, are approximate, and the gauge symmetries, if they emerge, are exact. The last element I would like to throw to the mix here is what happens when you add gravity. So there are very general considerations about the role of symmetries in gravity and whether we can or cannot have symmetries in gravity. And general considerations based primarily on black hole physics tell us that if we have quantum gravity, there cannot be any exact global symmetries. Quantum gravity does not tolerate exact global symmetries. So if we see any global symmetry in the real world, since we know we have gravity, we know we have quantum mechanics, we must have quantum gravity. So if we see any symmetry in the real world, it must be an approximate symmetry. So that's with global symmetries. Gauge symmetries can be emergent. In fact, it's widely believed that most of the symmetries that we see around us, the gauge symmetries that we see around us, are emergent. They are not fundamental in the fundamental formulation of the theory. But the key thing about gauge symmetries in quantum gravity is that all the charges must be allowed. If the symmetry allows us to have some charge 1 particles, some charge 2 particle, all of them should exist. There must be excitations with all charges, all electric charges and magnetic charges. I will later, every one of these slides will have a counterpart later in the talk. So this is the end of the first part of the talk. It was a lightning summary of the notion of symmetries, in various ways symmetries could appear. And that brings me to the second part of the talk. That part is duality. So duality in its simplest form is two different descriptions, two different theories, or two different languages describing the same physical phenomenon. So we have some physical problem that we would like to describe, some system, and we have two languages to describe it, like telling it in English or in French or in Hebrew. And these are different stories telling different ways of telling the same story. And the simplest example is we just perform Fourier transform. So this is the Hamiltonian of the harmonic oscillator, and if we classically just change variables from Q to P in this form, the Hamiltonian doesn't change. In a quantum theory, Q and P cannot be simultaneously numbers. What that means is to do a Fourier transform. So we can take the wave functions of the harmonic oscillator, Fourier transform them, and it's a property of the harmonic oscillator that the Fourier transform of the wave function gives us another, of the eigenfunction, gives us another eigenfunction of the Hamiltonian. So that's a manifestation of duality harmonic oscillator, and it's kind of overkill, because the system is already solvable. We know everything we want to know about the harmonic oscillator. Why do I need this complicated language? We need this complicated language because we can now move to somewhat less trivial examples. And the next trivial example, the next example up in the level of complexity is to look at free scalar fields. The first example would be in 2+1 dimensions. So take a free scalar field in 2+1 dimensions, call it phi. And if we just hit it with epsilon mu nu rho with d rho phi, that looks like some f like some field strength of a gauge field. So this is a Maxwell field in 3 dimensions, and a Maxwell field in 3 dimensions is the same as a scalar field. So that's another example of duality. A free scalar field in 3 dimensions, a free boson, is the same as a vector field in 3 dimensions. A slightly more interesting example is in 3 + 1 dimensions, where we can take Maxwell's equation in the vacuum without sources and replace E with B and B with minus E, or in a more covariant form, we write F mu nu as 1/2 epsilon mu nu rho sigma, F tilde rho sigma, and the transformation from F to F tilde, or from E to B, is a duality transformation. In the quantum theory, this is again some kind of a Fourier transform. And indeed, you can write Maxwell's equations without ever mentioning the vector potential. You can use E and B, and then the symmetry is manifest. A deeper idea is to use the vector potential. That allows us to solve 2 of the Maxwell's equations, and we are left only with 2 other equations. Then this symmetry is not manifest. If we use the vector potential, this symmetry that exchanges E and B is not manifest. When we use the vector potential, we have this gauge redundancy. They have different AMUs that lead to the same E and B. So we see an example of this gauge symmetry. But if we first perform this duality transformation, and then we have another AMU, call it AMU tilde, it has a different gauge symmetry. So what we see in these 2 examples, first of all, they're completely solvable. This is again an example that we can just write everything and solve everything completely, both classically and quantum mechanically. And one lesson from that is that in this description, we have a free boson, no need to have any gauge symmetry, and we can describe it as a gauge field with some field strength. And here in Maxwell theory, we introduce some gauge symmetry, but there are 2 ways of doing it. One with AMU, and the other with a magnetic AMU. So that's really a clear sign that the gauge symmetry is not fundamental. We have 2 different gauge symmetries in the problem. In this problem, we have 1 gauge symmetry here and no gauge symmetry here. And in this problem, we have 2 different gauge symmetries that we use. So none of them appears to be fundamental. So this example is slightly more elaborate than the harmonic oscillator that I had before. And over the years, people have found many more examples of this phenomenon of duality. I think the next one historically is Kramer-Vanier duality in the Ising model and various generalizations of it in higher dimensions, involving also gauge fields. Kramer-Vanier duality tells us that the Ising model at low temperature is the same as the Ising model at high temperature. And there is an exact solution of the Ising model, but regardless of the exact solution, you can easily establish that there is such a symmetry between the high temperature phase and the low temperature phase, and that symmetry has many, many consequences. Not only that, it also has many generalizations, especially to Ising model in 3 dimensions or even in 4 dimensions, so it's 2 + 1 or 3 + 1. So this is clearly a deep idea, and it's really a descendant of this duality that I mentioned earlier, starting with the harmonic oscillator. Over the years, many more examples of that were found, primarily in 1 + 1 dimensions, in the context of bosonization, conformal field theory, etc., and the examples still coming in. Perhaps the most beautiful example is an example of a field theory in 3 + 1 dimensions. This is a theory of gluons, very much like the theory of the strong interactions where we have gluons, except that it has a property called N = 4 supersymmetry. The details of that are not important. The only thing that is important is that this is a theory which is scale invariant. So if you look at the theory at short distances and at long distances, it looks essentially the same. It's based on some gauge bosons. There is some gauge group, just as we have SU3 of color. In general, we can put an arbitrary gauge group G, and there is a coupling constant, the same as the fine structure constant in electrodynamics. And the non-trivial fact about this theory is that we can start with gauge group G and fine structure constant alpha, and the theory is indistinguishable from a theory with another gauge group G tilde and fine structure constant 1 over alpha. This is extremely dramatic, because in the real world, alpha is small, and the success of electrodynamics is because the fine structure constant is small. It's 1 over 137. It's a very small number. And this is the same as the theory with a strong coupling. So if electrodynamics alpha were being very, very large, say 100, we would say we cannot use perturbation theory, we cannot solve the model, and yet there's another description of the same system where the alpha is 1 over 100, and therefore it's small, and it is solvable. The other nice thing about that is that it's very much like what we saw with Maxwell theory before. We had a transformation that exchanges electricity and magnetism, exchanges E and B. The same thing is true here. The gluons of one theory are the magnetic monopoles of the other. So it's again a phenomenon of exchanging electricity and magnetism, except that in Maxwell theory, that's an abelian theory, abelian gauge group, the gauge group is U1, and here the gauge group can be arbitrary, it could even be non-abelian. So going back to that, we have gauge group G with fine structure constant alpha. It's the same as G tilde with fine structure constant 1 over alpha. And this duality is an exact equivalence of two theories. So we have two totally equivalent, totally accurate descriptions of the system. We cannot prove it, unlike the previous examples. It's very much like this Fourier transform that existed in the harmonic oscillator or in the simpler example. In that sense, conceptually, it's easy, but explicitly we cannot prove it. And yet it relates the system in a very non-trivial way. The two different systems of the left-hand side and the right-hand side of the duality have the same spectrum of states in the Hilbert space. The Hilbert space is the same on both sides, exactly as in the harmonic oscillator I discussed earlier. The same spectrum of states, the same spectrum of operators, the same correlation function. So if you know how to solve one of them, you also know how to solve the other. And as I said, it exchanges weak coupling and strong coupling. So if the coupling constant is weak, if the coupling constant gets strong and the theory becomes complicated, it's the same as another system which is not that complicated. In terms of the quantum mechanical fluctuations, in one framework, the quantum mechanical fluctuations are small. In the other language, the quantum mechanical fluctuations are large. This is again something we are familiar with in the case of the Fourier transform. If we have a particle which is localized in position, its wave function in momentum space is spread out and vice versa. So we should always use the description of the system which is easier, and the easier one is the one which is more semi-classical, the one that fluctuates less, the one where the coupling constant is small, but that's useful because it allows us to describe the system even when the system is quite complicated. So continuing to discuss that idea, we have gauge symmetries in the two sides of the duality. And we have the different gauge symmetries. It might even be different gauge groups. On one side it could be one group, and in the other it could be another group. And just as in Maxwell theory, we saw different gauge symmetries, here we also see different gauge symmetries. So we ask ourselves, which of these two gauge symmetries is really fundamental? Is one of them fundamental or the other? And the more likely answer is perhaps neither one is fundamental. We have two different descriptions, none of them is better than the other, and we shouldn't view the gauge symmetry of any of them as being fundamental. We could also ask which gluon is the fundamental gluon. Which gluon is the elementary one, is which one is composite. I said that one of them is like a magnetic monopole, as the other is like a particle. And since we have two different descriptions, where the elementary degrees of freedom look different in the two languages, we ask ourselves which of them is more fundamental, and the question doesn't have an answer because the two are totally indistinguishable. So then what that means is the notion of elementary particle is ill-defined. We cannot say what's elementary and what's composite because in different frames, what looks elementary might look composite. It's like a different frames in general relativity. All of them are equally good or all of them are equally bad. There's another notion of duality. The previous examples were exact dualities, where we had two different systems which were totally indistinguishable. The second notion of duality is the duality is not exact. It becomes exact only at long distances. In other words, we have two quantum mechanical systems with their Hamiltonian and Hilbert space and so forth, and the long distance or low energy excitations of the two spectra of the two systems are exactly the same. So we have two different systems. The Hamiltonian is different. The spectrum at high energies looks different. But at low energies, the theories are totally indistinguishable from one another, from one to the other. So we can have one Hamiltonian at short distances. In condensed matter physics, this would be some system of electrons with some interactions between them, It could be very complicated. The electrons interact with each other. They interact with the ions at the sites, and it's hopelessly complicated. At long distances, we have an effective Hamiltonian that describes the physics at very long distances. And we have a flow between them. And we say this is kind of we call it a renormalization group flow. The system at short distances is described by one system, and at long distances is described by another system. An example is to look at molecules of water. We have lots of molecules of water, and they move around, and the degrees of freedom are the positions of the molecules as they move around. This is a very, very complicated system, totally beyond belief whether we can solve it, that we could solve it. And yet we can describe, we say we don't care where every molecule is, we are only interested in the shape of the water. So there's a wave of the water or there's some flow. So instead of talking about the coordinates of the fundamental molecules as the degrees of freedom, we have a totally different description. The degree of freedom is the velocity field, and the equations that describe it is not the Schrödinger equation of the molecules, but instead it's some Navier-Stokes equation for the flow of the water. And we say that at short distances, we have a system of electrons, of molecules, et cetera, but it contains too much information. We don't care about that. What we really care about is the effective description at long distances, which uses hydrodynamics or Navier-Stokes equation, and that's this flow from short distances to long distances. So that gives us to this So there are many other examples of the same phenomenon. In the simplest case, the degrees of freedom at long distance can easily be identified using the degrees of freedom at short distances. So an example would be the Landau-Ginzburg description of superconductivity. In superconductivity, we start at short distances with some electrons and phonons and all that. And in the Landau-Ginzburg description of superconductivity, we use kind of a bound state of two electrons. We call it the Cooper pair. And we write a theory where the degrees of freedom are just the Cooper pairs. And we don't need the rest of the details of the system at short distances. Another example is QCD. At short distances, we have quarks and gluons, and they interact in a very complicated way. At long distances, we see only pions. These are the light degrees of freedom at long distances, and they give us a good description at long distances. So these are examples where at short distances, we have some degrees of freedom, and at long distances, we have degrees of freedom that are related to them in a simple way. The Cooper pair in this example is roughly a bound state of two electrons, and the pion at long distances in this example is roughly a bound state of two quarks. So in these two examples, the degrees of freedom at long distances are related in a simple way to the degrees of freedom at short distances. That's not typical. The more typical situation is the degrees of freedom at long distances are totally different than the degrees of freedom at short distances. I've already mentioned the example of molecules in the water being the degrees of freedom at short distances. And at long distances, the velocity field is the degree of freedom. It looks like totally different. It's a complicated expression in terms of the microscopic description. In most cases, we can't even write it explicitly. And more than that, we don't even care to write it explicitly because it's not interesting. The solution of the problem is just to identify the right degrees of freedom at long distances and to find their effective description. When the degrees of freedom at long distances are non-locally related to the degrees of freedom at short distances, we can have much more interesting and richer set of phenomena. And examples are various phenomena of emergent gauge symmetry that I mentioned before, idea of particle-vortex duality in 2+1 dimensions. There are emergent gauge fields in the fractional quantum Hall effect, and the list goes on. So in order to be a little bit more explicit, let me now focus on 3+1 dimensions and give some review of what can happen with interacting gauge theories in 3+1 dimensions. So at short distances, we start from some gauge theory. That means some gluons, and there might be some quarks, and they interact, and it could be very complicated. And at long distances, there's a menu of options, various things that can happen. One of them is known as infrared freedom. We find the same theory we started with, it just becomes more and more weakly coupled as we approach the long distances. That's what happens in quantum electrodynamics. The second possibility is there is a non-trivial fixed point. This is what's known as a scale invariant theory or a conformal field theory at long distances. The notion of particle is not well defined. We can also find some approximately 3 degrees of freedom, some bound states, and the canonical example or the typical examples is pions in QCD. And we can also have a gapped system, namely there is nothing at long distances. So we start from something complicated at short distances and we go to long distances and the system is gapped and there are no long distance excitations. And all these options can be realized in theories like QCD if we change the gauge group, we change the number of colors, we change the number of flavors, et cetera, et cetera. So there's a very rich spectrum of possibilities, and my gut feeling is that we haven't even seen all the possibilities that exist. This menu is what has been found so far. And there are situations we can actually analyze it exactly. I'd like some extra time for the time I waste with the clicker. Okay, so an example of theories which have supersymmetry, the fact that it has supersymmetry is not essential for that, except that in this case we can actually prove what we are saying. We have 2 different theories. Call one of them electric, call one of them magnetic, very much like what we had before in Maxwell theory or in other examples I mentioned. And we can start with any of them at short distances. They are really different theories at short distances. And they both flow to the same behavior at long distances. This is the notion of duality I mentioned before. 2 different systems at short distances flow to the same system at long distances. If the system at long distances is boring, like it's gapped and there's nothing interesting there, this statement is not that exciting because we have 2 complicated systems that give us nothing at long distances. Not a big deal. But it's more interesting when they give something non-trivial, and these 2 theories give us the same behavior at long distances. Trivial examples of that is what's known as universality in condensed matter physics, but this is much broader than that because we can have the degrees of freedom here and the degrees of freedom here have nothing to do with each other. They are really non-locally related. They are really different. The second option is slightly more interesting. We can have some electric theory at short distances, some gauge group, gluons, quarks, etc. And at long distances, we have an approximately free theory based on other gluons. So in condensed matter physics, we formulate the problem at short distances, and the answer is what happens at long distances. A typical problem in condensed matter physics is here are some electrons, these are their interactions, these are the ions that sit there, and you put some impurities and this and that. Question, what does it do? Answer, it's a superfluid. Answer, it's a superconductor. It could do all sorts of marvelous things. The answer is what appears here, and the question is what appears here. So with this notion of duality, the question is dual to the answer. In other words, the degrees of freedom here is dual to the degrees of freedom here. And what we can see here at long distances, this is the solution of the problem, is some gluons which are bound states of the gluons here. But they are not bound states in the sense that we can say that one gluon here is a bound state of 2 gluons there, because the transformation between them is non-local. The degrees of freedom here are non-locally related to the degrees of freedom here. So at short distances, we see one theory, and at long distances, we see another. A simple example of that is like in ordinary QCD, we see quarks and gluons at short distances and pions at long distances. But in this case, we can even get some non-abelian gauge fields, some totally new QCD tilde theory, some totally different theory, which is related to the first one in a very complicated way. And its gauge symmetry is emergent. It turns out that there are many, many examples of that. This is a very ubiquitous phenomenon. And such dualities and emergent gauge symmetries are ubiquitous. And I think it's clear from that, for one thing, that gauge symmetry cannot be a fundamental concept. It's an extremely useful concept, but it's not fundamental. It's not fundamental because the gauge symmetries can come and go. And we can even find gauge symmetries in the answer that are not present in the question. So we always think that the question is fundamental and the answer is what we have to do, what we have to solve, but what's really fundamental at short distances might not have that gauge symmetry. So this is the second part of the talk. I talked about symmetries and about duality. Now I'd like to put them together, and I should have used the other computer. And that's the topic of putting them together and discussing the unity of physics. I'd like to flash just one slide, just for completeness, so that it does not appear like I didn't mention it. Is a huge topic of dualities in string theory and quantum gravity. So far we had the duality between two different field theories. We can have duality between different string theories, and they come under different names and different categories. There's also a huge field of duality between strings and fields with very interesting, marvelous results. I will not have time to discuss it here, so I just flash it here, and I encourage you next year to invite somebody who can give a talk about any of these topics. But I would like to switch to another notion of duality that appears also, that grew out of all these ideas, and this is duality between bosons and fermions. So in its simplest form, in its first form, it appeared in 1+1 dimensions, where we have a system of bosons which turned out to be equivalent to a system of fermions. This might appear surprising. The bosons have integer spin, and the fermions have half-integer spin, but particles in 1+1 dimensions do not really have spin, so that's not an objection here. It's still very surprising because bosons are commuting and fermions are anti-commuting. So how can we have a system of bosons which are commuting and create out of it a system of fermions which are anti-commuting? And the answer is again this marvelous non-locality. A non-local transformation can take something that is commuting to something that is anti-commuting, and vice versa. So this is something that was done in the second half of the 20th century. It's fully understood that systems of bosons and fermions could be indistinguishable in 1+1 dimensions. Later, people looked for similar phenomena in 2+1 dimensions, and it comes under various names. The simplest form of it is that we take a massive particle, a single massive particle, which is, say, a boson, which has spin 0. So it's a single spin 0 massive particle. We couple it to a gauge field with certain interactions. Technically, they're called Chern-Simons interactions. That doesn't matter. And by doing that, the massive boson starts acting like a fermion. And we can also do the opposite of that. Take a massive fermion, couple it to some interactions, and the fermion starts acting like a boson. As it changes its statistics, it also changes its spin. So we can take a particle with spin 0, couple it to this interaction, and it behaves like it has spin 1/2, and the other way around. So this is known as statistical transmutation or spin transmutation. And it has been extremely powerful and useful in the context of the fractional quantum Hall effect, when the name that comes with it is flux attachment. We take a particle which is a boson, we attach to it some flux, and then it starts behaving like it's a fermion, or the other way around. So this is an example of bosons-fermion duality. A system of bosons is the same as a system of fermions, and the relation between them is non-local and therefore interesting. Now, in the last several years, there's been a lot of work about finding many more such boson-fermion dualities. This is mostly work in the last few years, and this is the only slide in this talk where I put references. If the projector had been better, you could have read the references here. And I would like to highlight Aharoni's name because you see his name appears all over the place here, and especially in one of these papers. He really made the fundamental contribution here. And this is not the same Aharoni I mentioned earlier in the talk when I mentioned the spectacular quantum mechanics course that I took here, but they are related. So the typical example here is that we take a system of fermions or a system of bosons, we couple both of them to gauge fields. So these are different systems, different Hamiltonians, different Lagrangians. We have on one side fermions coupled to some gauge fields, and on the other side bosons coupled to some gauge fields. And at long distances, they become indistinguishable. So this is very similar to the slide I had before of two different theories at short distances flowing to the same non-trivial theory at long distances. And another version of it is the more interesting one, where we start from bosons and gauge fields at short distances, and at long distances we find free fermions. This is, again, what I said before. At short distances we formulate the problem, at long distances we read off the answer. So this is a very complicated system. It has bosons and gauge interactions and gauge fields, and they interact. It's very nonlinear and very quantum mechanical. The quantum fluctuations are very large, and at long distances, we find free fermions, which are exactly solvable and really simple. And it's very surprising, how can a system of bosons, doesn't matter how complicated it is, and doesn't matter how strong the interactions are, how can it spit out a free fermion? How can where will the spin come from? Where will the statistics come from? Well, that's what makes it so exciting, and that's what makes it so interesting. Unlike the example of the harmonic oscillator or Maxwell theory, in all these examples we cannot perform the transformation explicitly. We don't have such a Fourier transform that takes us from one system to the other. But we have a lot of reasons to believe that this is right. So where did this whole thing come from? I just stated the fact that one theory is the same as the other. It turns out that all these dualities came from a confluence of ideas from different branches of physics. And I actually find that particular aspect particularly exciting. Ideas that came from totally logically independent lines of research in different subfields of physics, physicists in fields that rarely talk to each other, came up with similar ideas that not only are either the same or better, complement each other, and give us more confidence in the bigger picture. So I mentioned earlier in the talk various dualities in supersymmetric theories. In supersymmetric theories, we can perform a lot of tests, a lot of things are calculable, and if we conjecture a duality, we cannot prove it, but we can perform many, many tests of it. I also mentioned some string dualities, and again, they are connected to the supersymmetric ones, and again, there are many tests. A third line of investigation came from also something I just mentioned briefly, ADS-CFT. It's a topic for a totally different seminar, but this is a case where we have some bulk theory with gravity, which is dual to a theory on the boundary of space-time, which doesn't have gravity. And the examples here where the same bulk theory had two different boundary theories. If the same bulk theory, the boundary theory should be the same, we can forget about the bulk, and we have, again, a duality between field theories, which can be checked explicitly at large n. So this whole thing, if you don't know any of these things, don't bother. I'm just listing here a long laundry list of examples, different subfields of physics. The people in this thing did not talk to people saying condensed matter physics. They all thought that they're talking about different things. I'm not interested in what the people in the other field are doing, even though they're in the same corridor. But they all came up with similar ideas that complemented each other, especially they're putting it all together with the condensed matter literature, and a rather coherent picture emerged, which is the one I summarized before. And we can perform many checks on these suggestions. So first of all, we can derive many, assuming that these dualities are right, we can use them to derive many known results. That's not a strong check, but it could have failed and it didn't fail. So we can relate also to dualities that were conjectured and were subject to many tests. There were also relation to ideas in mathematics, notion of mirror symmetry, which is important in topology, and level rank duality that appears in various other branches in mathematics. And the dualities are not independent. We refer to it as a web of dualities. If you take one of these and you assume it's true, you can derive many others. And then you can take another one, assume it's true, and you can derive many others. So anything that goes wrong in any of these dualities, the whole logical structure falls apart. And the fact that we have so many dualities and it could have fallen apart so many times and it hasn't happened gives us more confidence that this is right. Of course, this is not a replacement for a rigorous proof and a deeper understanding of why it is true, but we have no doubt that all these dualities are true. So first of all, it is interesting in its own right that we have theories of bosons dual to theories of fermions that give the same physics at long distances, but it also has kind of more pragmatic, more practical applications, especially in condensed matter physics. It has applications in the fractional quantum Hall effect, in the physics of the first Landau level at half filling, theory of known as HLR, and it's connected to that, and to gap phases of topological insulators and topological superconductors, and maybe we'll hear more about it later in the afternoon. So this whole notion of dualities between bosons and fermions seems to be connected to ideas in quantum gravity on one side, the study of supersymmetric field theories in another, and to some topics in condensed matter physics, So I really think it's fit to call it the unity of physics. We are all doing the same thing, we call it differently, but these are all the same basic ideas. I would like to end with one more slight discussion of comparing symmetries in quantum gravity and in condensed matter physics. And again, two almost as remote topics of physics as you can imagine, very abstract quantum field, quantum gravity, no experimental consequences, and a very experimentally rich subject like condensed matter physics. So I've already mentioned the fact that there are no global exact symmetries, no exact global symmetries. In gravity, it came from issues associated with black holes. In condensed matter physics, if we start from a system that at short distances doesn't have any global symmetry, any new global symmetry, at long distances there shouldn't be any new global symmetry. There might be approximate symmetries at long distances, but not new one. And that's not that different than the ideas that we see here in quantum gravity, and for totally different reasons. These two reasons have nothing to do with each other. Second, we can have emergent gauge symmetries. So in quantum gravity, we can have emergent gauge symmetries. And I mentioned before that these emergent gauge symmetries, if they exist, all allowed charges must be present in the spectrum. This follows again from physics of black holes. So every charge that is allowed, there must be a state in the Hilbert space which carries that charge. We cannot say that only even charges exist. That would be inconsistent. The same thing is true in condensed matter physics. If we have an emergent gauge symmetry, all allowed excitations must be present in the spectrum, otherwise we reach an inconsistency. So this similarity or this analogy strikes me as very peculiar. Two different branches of physics, the reasoning is totally different, and the conclusion is the same. So the conclusions both about global symmetries and about gauge symmetries is the same in these two different branches of physics. I feel that there's much more to say about that, but I don't have anything useful to say. So let me summarize the talk. So if you fell asleep, that's the time to wake up. Symmetries are common in physics. We have known that long before the talk. It started in the 19th century, 20th century, and I think they will dominate 21st century physics. Both in quantum gravity and in condensed matter physics, we saw that there are no exact global symmetries. Gauge symmetries can be emergent. In that case, they are exact, and all charges must be present. And again, I emphasize this unity of physics, same conclusion, different setup, different reasoning, the same conclusion. So this must mean something. We mentioned dualities. Again, they are common in physics. We've seen examples of that in different branches of physics. This is the idea that two different descriptions of the same physics. So in the early quantum mechanics, people used the word of particle-wave duality. Neither of them is precise. Here we're talking about two precise theories, two precise languages giving us exactly the same physics. And again, I want to emphasize the unity of physics. Similar ideas arising in different branches of physics, and in the example of 2 + 1 dimensional dualities, this was a convergence of ideas coming from condensed matter physics, quantum gravity, study of supersymmetric field theories, and others. And it has led to better understanding of known phenomena and known mechanisms, and also predicted new phenomena and new mechanisms. More generally, we talked a lot about gauge symmetry. I emphasize that the gauge symmetry cannot be fundamental. If it can be emergent, it cannot be fundamental. That's a general thing. What is emergent cannot be fundamental. It could be useful, it could be important, but it will not be fundamental in the sense that the final theory of nature will be based on that principle. So it's often convenient to use it, but it cannot be really fundamental. And that suggests that we should really look to a new formulation of field theory and of physics in general, which makes all these dualities manifest. We shouldn't be surprised by them. We shouldn't be challenged by trying to prove them. We should just look at the formulation of the theory and it should be obvious why this is so. So I think this is a nice way to finish the talk here. We talked about the unity of physics and huge challenges that lie ahead. Thank you.
Any questions? Yeah, right there at the top.
Hi, Nati. If gauge symmetry is not exact, if that's what you're saying, means that the charge is not exactly quantized?
I'm sorry?
If you say that gauge symmetry is only emergent and it's not an exact symmetry, that means the charge is not exactly quantized at E, let's say for the proton and the electron?
Okay, what I said is that when a global symmetry is emergent, it's not exact. When a gauge symmetry is emergent, it must be exact. The reason the gauge symmetry, if it's emergent, is exact is actually because it's not a symmetry. It's a redundancy in the description. Redundancies cannot be approximate. Symmetries can be approximate. Redundancies cannot be approximate. So in the case of gauge symmetries, even if they are emergent, they must be exact, and therefore electric charge must be quantized. So it cannot be approximately quantized.
Okay.
Any other questions?
Right. So you said that you cannot prove your dualities, but they must be true. So I'm sorry, but why? I agree that it's a beautiful theory, and it would be very nice if the universe worked like that. But why should it? I mean, if we can't prove it,
I don't understand. Are you asking whether it's true, or are you asking
Yes.
whether it was proven?
You
These are
said
two
it
separate
wasn't.
questions. We're not mathematicians.
You said it was not proven, right?
Well, in the case of the harmonic oscillator, you can perform the Fourier transform, and you can prove it. In the case of Maxwell theory, without sources, you can do it exactly, and you can prove it. In the case of the Ising model and its cousins, you can prove it. And then in the other cases, there is a hierarchy of things that you cannot prove any of them rigorously. In fact, in quantum field theory, you cannot prove anything rigorously. Mathematicians tell you that quantum field theory is ill-defined. And if we just say that we're not talking about things that are rigorous, then 90% of what physicists do is not rigorous. So that's not a good attitude to take. But in the case of the dualities, some of them are on stronger footing than others. It's a web of conjectures. It might be that logically, it might be that all of them are wrong. What can be proven is that if you assume some of them, let's assume one of them is right, we can prove many others. And there are many subsets that we can, let's assume number 1 and number 5, and then you can prove 7, 8, 9, and so forth. And some of them have consequences which are highly, highly non-trivial. Deep results in mathematics that nobody anticipated just came out of this collection of ideas. Things that mathematicians couldn't do before. New ideas in physics that just follow from that and people didn't anticipate before. So all these things really hang together in a beautiful way, and it has been going on for decades with lots and lots of checks. It's true that some of them are on stronger footing than others, and it might be that some of them are wrong and others are right. My gut reaction is that the vast majority of them, if not all of them, are right. And proving them, I should emphasize, is not just a nuisance. It's not just, well, we haven't proven it rigorously. One attitude would be, let's dismiss it altogether, and the other extreme was, if it's not proven, I'm not interested. I think the correct attitude is the third one. It's probably right, and we should attempt to prove it, because if we can prove it, I can guarantee you that we'll get really fundamentally new insights about physics. So many different things hang together on this whole set of conjectures. Many things that we believe are right, but we cannot prove. There is no doubt that if a proof will come, it will come with new ideas, new ways of thinking about things, which will be extremely useful and productive. There was a question here.
Can you elaborate on your statement that there is no spin in one dimension? You said it very briefly, that in one dimension...
Yeah, if you take a particle in one dimension, in space. There is no spin because you cannot rotate anything. If you have something, a particle moving on a line, a bead on a string, it cannot rotate.
Okay. So it doesn't prevent having a real physical spin chain in the laboratory.
When you say spin chain in the laboratory, the spin in the laboratory is just a bit, which is either plus or minus 1 on each thing. It has nothing to do with rotations. When people discuss in the lab a spin chain in one dimension, when the word spin there is misleading. It's not spin in the sense that the thing is spinning. It's just the fact that this is a two-level system that has two states.
But we learned that the spin of the electron doesn't come from its own rotation. It's a property.
Well, this is a deep idea. So there's the rotation that exists in space, and then there's the rotation of the spin. And in many cases, they are essentially the same. In the example of the spin chain in one dimension, nothing rotates there. There's a two-level system at each side of the lattice. When you say spin chain, that's what you mean. There's a two-level system at each side, and it has nothing to do with any rotations, because there cannot be any rotations in one dimension. In higher dimensions, you can have it, and when you can have it, say, in 2 dimensions or in 3 dimensions, there's a rotation group. There are representations of the rotation group, and they give these two-level systems. That's why it's called the spin chain. But it is true that the spin chain is a misleading name. But everybody uses it, so it's too late to change the terminology.
One last quick question before we move on. Okay, so let's thank Nati Seiberg again.